Now we are going to go to the next topic, which is the topic of 5.3. Now we will formally venture into the definition of integration. So now there is this very important idea that if you have a function which is continuous on a and b, you can always try to find its remaining sum. Okay. Now, if the remaining sum of a function exists, then you say the function is integrable. Okay, this is just an definition of the term integrability. Let me say it again. If you have a function over an interval, you calculate its remaining sum using the painstaking way I mentioned just now. If the limit of the remaining sum exists, then you say that function is integrable within that interval. And then if a function is integrable, it will mean that the remaining sum of the function p of k delta k equals to 1 to infinity. This sum exists, and if limit exists, then we say the function f is integrable. And the limit of the remaining sum, here we represent the number or the values of the limit of the remaining sum by I. So here I is just a number. That means it represents the finite values of the remaining sum. And sometimes we represent the limit of the remaining sum by an symbol, which is going to be plain here. So if a function's remaining sum exists, then we represent the integrability of the function by a symbol. Okay, so here I have a function that is integrable between the subintervals of a and b, and the function is continuous. And if this function f is integrable, then I represent the limit of the remaining sum by this symbol. So I equals this symbol represents the values of the integral of the remaining sum of the function. So in this case, f is a continuous function, then this symbol represents the definite integral symbol. Definite integral. The definite integrals of the function f between the lower limit a and the upper limit b means that this function is integrable, and if it exists, then its value is equal to the remaining sum. So when you see this symbol f sitting inside an indefinite integral between the two limits, then the first thing that comes to your mind is that this represents an remaining sum of the function within the intervals of a and b. Okay, that is the definitions of the definite integral table. Okay, so it is the symbol that we use to represent the remaining sum of a function, and if that remaining sum exists, then we say the function is integrable. Okay, so this is just the anatomy of the definite integral symbol. And sometimes when you see this, we say this is the integration of the function from a to b. Sometimes we also call this an integral of the function f from a to b. Sometimes we just call this the definite integral like this. So in this case, sometimes integral or definite integrals refers to the same thing. So up to this point, I just want to introduce to you the symbols of this definite integration. Now you look at this definite integration a little bit more closer. It looks like this. It is actually quite familiar. It looks like someone, right? It looks like what? It looks like the symbol for antiderivative. Remember the antiderivative I mentioned this morning? Antiderivative is like if you have a function, the collections of all the possible antiderivatives of this function f is represented by this. This is called the indefinite integral. This is called the definite integral. So the indefinite integrals and the definite integrals looks very similar. It's just like someone who have a missile and someone who have no missile, but it looks exactly the same other than that. But these two are totally different things, right? These are totally different things because indefinite integral represents functions, collections of all the antiderivatives, whereas the definite integral represents a number, which is the Riemann sum of a function. Okay, so these two should be considered as totally different pieces altogether, and you cannot equate them together, right? You cannot, because in principle these are two different things. Although it looks very similar, but it is a totally different thing. Okay. So then we go to this very important theorem. It says if you have a function which is continuous between a and b, then it is guaranteed that the function must be integrable. Right? Not all functions are integrable within an interval. For example, this kind of functions, which is very weird. Right? This kind of function is not integrable because it is not continuous. For most of the functions that we encounter, for most of it, most of the functions we encounter are integrable, especially if the function is continuous within that interval. That according to this theorem 1, it must be integrable, meaning that its Riemann sum must exist. So this theorem only says if you have a function, its Riemann sum must exist, because the existence of the Riemann sum for the function is just equals to the statement that the function is integrable. Okay, so sometimes you say the function is integrable, sometimes you say the Riemann sum exists. Both of them actually refer to the same thing. So there are sometimes you are not sure because the sum of the function may or may not exist. But this theorem says as long as the function is continuous, definitely it is integrable. So with this theorem, then you feel more confident. Every time people give you a continuous function, you're very sure that its Riemann sum must exist. But then the problem is, what is this value? Right. So I said, someone here who is the richest person in Malaysia. Yeah, who is it? You don't know who it is, but there exists one. This is just an example, okay? So in mathematics, you always have a proof for the existence, but you don't have a proof for what value it is. Okay, so you have to first prove its existence before you zoom in to find out quantitatively what its value is. So theorem 1 only guarantees functions to be integrable, but it will tell you what is its Riemann sum. So what we are going to do next is to try to learn up some tricks or some tools that allows you to calculate the Riemann sum of an continuous function. Okay, so this is like the definition. This is like what we did in the study of the derivative. Remember, in derivative, you learn that the derivative is a process of limit taking. And then if you were to calculate the derivative of a function using the definitions of derivative taking, then you find that it's very painful. Calculating the derivative function using definition is always painful. So you learn many different theorems, many different tricks that allows you to easily evaluate the derivative of a function. So likewise here, you would start to learn some of the useful tricks that allows you to evaluate the Riemann sum or the definite integration of a function. So this theorem too is very useful. It says if you have two functions which is known to be integrable, then they follow these rules. So if you know any of the definite integral of f of x, sorry, no. This is a different. I will talk about that in a minute. So yeah, so if assume that you know the definite integral of f and the definite integral of another function g, then you can use the knowledge of the values for f and g to evaluate the integrals or the definite integrals of any other function. For example, the first of the theorem, let me explain a little bit of this of the first of the theorem. It says if you have a function that is like this, and then you know what is the definite integral. So this is to sum up from A to B. Okay, to sum up the function to make the partition with A to B. So now if I ask you what is this, go from B to A. Okay, so this is a different story. Here we assume that A is smaller than B. So here A is smaller than B. So when I write down this statement to define the partition, the lower limit is sitting on the left of the upper limit. What happens if you reverse the lower limit and upper limit of A and B, where B is still larger than A? Okay, so here A is smaller than B, and this is the case where B is larger than A. So according to the theorem, the values of this definite integral is the same as the definite integrals of the function from A to B with an minus sign. Now this is given to you, and it's not proven. But we are not going to go through the proof for each of the rules here. So you have the second rules. If the lower limit and upper limit in the definite integral is equal to the same, that amounts to not defining any area of the curve. Like so, in order to define the area of the curve, you must always have a width which is finite. This is the area of the curve, which is defined by the width. Like the width is just the difference between A and B. If A and B are the same, that would mean that the width will become zero. If the width becomes zero, then we would not ever define any area for the column anymore. So that is one way to understand the rule number 2. The integrations or the definite integrals with an zero width always end up to be zero. So then we have another rules. If you have a function f of x, and then you know what is its value, okay? You know what this value is, then you ask another question. Can you now form another function h from f of a by multiplying the function f with an constant k? Then you ask what is the values of the definite integral for the function h from a to b. So it turns out that according to the rule, the integrations of the function h from a to b is simply equals to the values of the definite integrals for f from a to b multiplied with the constant k. So this is what the rule was saying. And then there are also the sum rule, the different rules, the sum and difference rule, the additive rules, and the maximum minimum equality rules, and also the so-called domination rule. So all these rules can be understood from this picture. So this example is an example that tries to illustrate the applications of the minimum maximum inequality rule that will allow you to calculate this definite integral. So this example 3 asks you, what is the definite integral of this function, square root of 1 plus cos x for the lower limit 0 and upper limit 1? The question does not ask you what its value is, but the question asks you to show that its value is less than 3/2. So if you look at the maximum minimum inequality theorem, what it actually says is this: if you have a function that is continuous between two intervals a and b, then according to what we have discussed in the previous example, in the previous discussion, for such a continuous function between a and b, there must exist an minimum and there must exist an maximum. Right? Remember that function, that theorem. Therefore, there must be some values of f of max for the function within a and b, and there must be some number within a and b where the function is the smallest. Okay, so this theorem says if you have a function fx, you take the definite integrals between a and b, its value can be roughly understood to be equal to the area under the curve of this function. Okay, so this can be understood to be area under the curve by assuming that f is always positive. So then, can you see this quite easily? That is, the area under the curve always less than the larger box, but it's always larger than the smaller box. Okay, so this smaller box in green is just the product of f of minimum. So this is the height of f of minimum multiplied with the width of the box, whereas the larger box in red is just the product, the area is the product of f of max times the width of the box. Right? So it is always clear from the grammatical point of view that the functions not the function, the area defined by the indefinite integrals from a to b is always equal or larger than the small box area, but it will be less than the large box area, where f min and f max both refer to the maximum of the function within an interval and the minimum within the intervals. So with these conditions, then what we can show is this: look at these functions, 1 plus cos x square root of x. Then you try to find out what is the minimum of the function. Can you tell me what is the minimum of this function, square root of x, square root of 1 plus cos x? So cos x is a sinusoidal function. The maximum values of cos x is 1. The smallest is -1. Therefore, the smallest values of cos x is -1. Right? So when x changes, cos x will also change, but the smallest of cos x will be just equal to -1. So the minimum of the function is then just equals to 1 minus 1, where cos x become -1, so that will become 0. So the minimum of the function square root of 1 plus cos x is 0. And can you tell me what is the maximum of the function? The maximum of the function is just equals to the values when x is equals to 0. Like when x equals to 0, cos x becomes maximum. Maximum of cos x is 1. So the max of function is then square root of 1 plus 1, which is 2. 2 is 1 plus 1. When cos x is equals to 1, the square root functions become maximum. Therefore, I've then shown that the maximum values of the functions for this 1 plus cos x is definitely. So I'm looking at the integration of these functions, or the definite integrals of 0 to 1. um, this this value must be okay. So here I'm looking at the values of integration from between 0 to 1. Okay, so here is 0, here is 1. Okay, this is 1. So I have shown that between 0 and 1, cos, well, the maximum of the function is square root of 2, and the minimum is equal to 0. So in that case, this must be equals or larger than the width of the intervals, which is delta to 1 minus 0, which is equal to 1. So on the left hand side, the product is f of minimum times the width, which is 1, and the right hand side represents the values of the x f of max times the width, which is 1. And this is just square root of 2. Okay, so I have just shown that indeed the definite integrals of cos of x dx is larger, it must be larger than or equals to 1, and it must be smaller than this one. Okay, so what is square root of 2? This is 1, this is 2, this is 4. Okay, so if you square this, it become 2. So, but anyway, if you check the calculator, this is just 1.414, and so on. So, square root of 2 is a number which is less than 1.5. Right? So you don't know exactly what it is, but this is the number which is less than 1.5. Therefore, if the definite integral is less than square root of 2, then it must be less than 1.5. Okay, the reason is because 1.5, 1.5, yeah, for sure, because 1.5 is larger than square root of 2. So if this is less than 1.4 if this function is less than square root of 2, then definitely it is less than 1.5, right? So this is 1.5, this is square root of 2. So if the function is less than square root of 2, definitely it will be less than 1.5. So this is an example of inequality. Is the example of inequality. The question does not ask you for exact value, but the question just asks you to show that it is less than. Okay. So as I mentioned earlier on, if the function is positive within that interval, then the integral, the definite integral, would then represent the area under the curve of the function. For example, here we have a function y equals to x, and between 0 and b, then the definite integral of 0 to b for the function y then equals to the area under the curve. So this is the theorem that it says. So using this definition, then you can use these definitions to calculate the definite integrations of x integrated between 0 and b. Now, this example is a very, very simple, trivial example. Everyone knows this. Everyone knows what the values of this function is because you know how to perform the integration. But what I'm trying to tell you here with this example is this. We have not really known how to perform the integration yet. What we are looking for is to calculate the definite integrations of the function y integrated between the lower limit of 0 and b. So basically the question asks you what is the remnant sum for the function y equals to x lying between 0 and b. So this is what we are looking for, and we are supposed to calculate this definite integral using Riemann sum. But according to the definitions that is introduced here, it says as long as the area of, as long as the function is positive, then the area that is represented by the functions within the intervals would then be equal to the Riemann sum of the function over the interval. So there are two things here. First thing is the area A of this function between the curve and the x. So here A is the area of this triangle. So you can easily calculate the area of the triangle using the geometry you have learned in your secondary school. It is just equals to the height of the triangle multiplied with the base of the triangle times half. So the area A is then equals to half times the height, which is b. Like if the function y equals to x, then at the point x equals to y, then the height here is then equals to b. So b here refers to the height of the triangle, and the width is then equals to b. So we end up to have half of b squared. So this result is calculated not by using any Riemann sum, not by using any algebraic method, but this result is calculated simply by using geometry that represents the area of this triangle. Okay. Then according to this theorem that we mentioned just now, then according to the theorem, if the function is always positive within the subintervals of I, then this Riemann sum between this interval I is then equals to the area of the curve. And in this case, the curve area is easily calculated to be just half of b squared. So left-hand side here is calculated by using geometry for the area of this triangle. And once you have calculated this one, then you will be able to obtain the Riemann sum for the function of x running from 0 to b. Right? So it takes actually a very painful procedure to obtain the Riemann sum of this simple function y equals to x, a very simple function between 0 and b. Okay, so up to this point, what we have learned is you can actually use the area of a positive function to calculate the Riemann sum. You don't calculate the Riemann sum directly, but you calculate the area instead. Right? So you calculate the area. If the area is easily calculated, then you get the Riemann sum easily. Now this is another example where have the area to be given by a trapezium. Right? Therefore, the area of the trapezium can be easily calculated to be half of A plus B times the width of the trapezium. So the width of the trapezium is B minus A. So you multiply this whole thing by the width of B minus A. That will give you the area of a trapezium. Then you would then find that the functions of x integrated between A to B then is given by the area of an trapezium. So this is another example where you evaluate this Riemann sum of the function x integrated between lower limit A and B by using the geometrical approach of calculating the area. So here you use the area of a simple shape to help you calculate the Riemann sum. However, in general, if the function that you want to calculate for its Riemann sum is not a simple, does not give you a simple geometry interpretation. For example, if you have a function that looks like this, for example, a function that looks like this, then it would in general be difficult to use any geometrical rule to work out the area of this function. So the method I will just mention, using the area of a simple geometry as a way or a shortcut way to calculate the Riemann sum, would not be applicable for cases like this where the function does not represent a simple geometry, or you have a situation that looks like this, where the function within the intervals of interest has positive values as well as negative values. So in this particular case, also you cannot use the geometrical approach of calculating the area under the curve to represent the remnant sum directly. Therefore, this method of using the area to represent the Riemann sum of a functions only applies to very simple geometry, very simple function. Okay, so this example also tries to prove that the area of this triangle is indeed equal to the Riemann sum. Okay, so once you have established this proof, this example, then every time when you have an area, you can use the area of this function to calculate the Riemann sum for function which is positive. Okay, so before I leave this example, I just want to mention one more thing. Here in example 4, you calculate the area of the triangle using geometry. You also calculate the Riemann sum of this function using definition for x running from 0 to b. So you make partitions, you calculate and evaluate the Riemann sum, and finally, after you have gone through all this painstaking process of summing the interval, of summing these combinations, then finally you will arrive at this expression, and you find that indeed the Riemann sum for this function between 0 and b is equal to b squared over 2, which is exactly the same as you would obtain from geometrical consideration. Therefore, this example proves that the area of the function, which is positive, then represents the Riemann sum. But in general, if the function is more complicated than a straight line, then it will be difficult to prove the Riemann sum of such a function is equal to its geometry. Okay. So so up to this point, we have learned another trick, that is you use area to allow you to calculate the Riemann sum. And then these are also the other tools that allows you to calculate the Riemann sum if the Riemann sum for some functions are already known. Then this is the third trick that allows you to calculate the Riemann sum of two very simple functions. So here the theorem says if you have a function which is a constant, then the Riemann sum of a constant function between limit a and b is just simply equals to c times b minus a. And this result is actually obtained quite easily by using the geometrical interpretations of area that we discussed here. Right? So here we have mentioned the area under the curve of a function is equals to the Riemann sum of the function. So in that case, if you set fx to be a constant, then you can easily see that indeed this is true. Okay. So this is a very trivial and simple result. Let's say the Riemann sum of a constant between a and b is just the constant times the difference in the limit. Then the next theorem is this. You have a function x squared, and you find the Riemann sum for this function between a and b. That gives you an value which is equal to the x cubed b cubed minus 3 minus a cubed over 3. So this is again another result that is given to you. So we have also seen in the previous example, if you have a function of y equals to x and you evaluate the trapezium defined by the constant between a and b, for the functions of x between a and b, that will give you b squared minus a squared over 2. And that is just the equals to this is just equals to b minus a times a plus b over 2. Okay, the area of the trapezium. So we have seen these results in the previous example, and then in this particular theorem, we have learned this simple result. And then we are also told that the Riemann sum of x squared between A and B is given by this. We have not proceeded to prove this, but in exam, for example, it asks you to prove this. Everyone knows this result. X squared integration from A to B is B cubed over 3 minus A cubed over 3. Everyone knows the result. But if I ask you to really prove this using the definition of Riemann sum, it will be actually quite challenging. Last time we discussed how you prove these statements, but I think in this time I don't do it anymore. Okay, so with this with these results, you would be able to calculate the Riemann sum for some simple functions, such as I think such as for this example. So I run the example. Okay, so up to this point, I hope you can appreciate the few things I mentioned here. Now, these are very simple results. Most of you know this since secondary school, okay? But it actually has a lot of meaning behind it. This is obtained by using Riemann sum, and you have to prove these simple results before you can use it. But when you use it, you don't care where it comes from, but it actually comes from the definitions, which is not as simple as it appears to be based on the form of this function or of these results. Okay, so before I end this, I would like to spend a little bit of time to talk about this average mean value, which is just very simple meaning. It says we have a function which is continuous between A and B. Then you have a function phi between A and B. Function may be like this: y equals to f of x. Then the definite integration of the function between A and B, it must be equals to something. Now, what is this equals to? Can imagine that this function, assume that f(x) is always larger than, assume that it's equal or larger than 0, and between A and B, the integration then defines an area of A. When A here refers to the area of the curve. Now, imagine that the area of the curve is a positive number, then it is possible to find another values which we call, say, this number. Say f placed in a pointed bracket. So this f in the pointed bracket, sometimes people also write this in the form of f bar. This is a number. So imagine that you calculate some number such that the area defined by the green color box has another area which is equal to the values of f bar multiplied with the width of this b minus a. B minus a, such that this product gives you the values of a. Right. So here I start off defining values of a to represent the area of the curve between A and B, which is this area. And you can imagine that this f bar define a constant on a box where the size of the box is equals to the area of A. Right. So if you can find such a number of f bar, then f bar is then the average value of the function of integrations of f between A and B. So that is what we meant by the average values of the function. So if I give you a function, then I ask you to calculate its average value. over an integral, then how do you calculate that? So you calculate that by imagining that the value of alpha multiplied with the width of the interval is equal to the area of the function defined between A and B, right? So here is the area of the box represented by the constant of alpha. Then this represents the area of the function, which is generally curved. So if I give you a function f, you can then calculate the average values of the function by using this very simple definition. So here is a very simple example of calculating the area, the average values of the function given by square root of 4 minus x. So to calculate the average value, you just have to multiply the average value, which you try to find, with the width of this function between a and b, which is equal to 4. Right? 4 is the width, that is 2 minus 2. Then the area defined by this, then just be equal to the integration of this between minus 2 and 6. Therefore, you can then easily calculate the values of this integration. Then you get the values of the y bar. So here, the y bar, let me try to do it again very fast. So I have minus 2 and I have 2, and this is a circle with a radius r equals to 2, and I'm looking for its average value. So the average value of f bar multiplied with the width of this 4 is equal to the area of the function defined between minus 2 to 2. So here, this is just the area of the circle. Okay. So how do I calculate the indefinite integrations of this function f, where the function of f is a complicated function of 4 minus x squared? Okay. So to calculate this integration, it's actually not easy if you use the definitions of the Riemann sum. But as we discussed just a minute ago, the integrations of this function over minus 2 to 2 is just can be calculated to be the area of this curve. And what is the area of this curve? The area of this curve is half the size of a circle. And this circle has an area, has a radius of r. Therefore, the area of the semicircle is just equal to half of the circle, which is 5 squared. So here, the pi r is 4, r is 2, so you have equal to 2 pi. So 2 pi. Therefore, the definite integrals of this function from minus 2 to 2 can be easily calculated using the geometrical approach, which is equal to 2 pi. Okay? So then the answer for this question becomes straightforward. Average of the functions 4 minus x squared in the square root is just equal to 2 pi over 4. And this is the width of the base from minus 2 to 2. Then this is the f bar, which is 2 pi. So that illustrates how you can calculate the average of the integrations of the function. Okay, so here we are talking about the definitions of the average of or mean value of a function. Okay, so next time I give you a function, ask you to calculate the mean value. This is how to calculate the mean value of a function. Now, before I let you go, I'm sorry, kind of wrong. You actually have seen this before in your physics. Right? So remember if you still remember your root mean square value, so in our two-sided function of an AC circuit, remember if you have an AC circuit, then you have this formula of V naught over square root of 2. Okay, remember this? You learned that. So the definition of the root mean square value is actually derived from this definition, where you assume your function of the sinusoidal functions is like this. When you change with respect to time, then you calculate the average values of the function for a full period. So that divided by 2 pi, that give you the average values of your sinusoidal functions squared within the period of 2 pi. That gives you the average of the v squared. When you take the square root of the average of the square, then we get this called v root v squared. Okay? Okay, I think you cannot stand anymore. I'll let you go, and I'll see you tomorrow morning. Okay?